Next, let's talk about shear stress and shear strain. When talking about shear, instead of using P, we use V to denote the shear force. Notice that in the previous section, we talked about direct stress. That means P is normal to the surface where the force is exerted, right? Those two forces are perpendicular to the applied load P. But this time, since we are talking about shear stress and shear force, it is different from the direct stress. As you can see here, if we have a prismatic block with its bottom fixed, then if you apply the shear load V, the V is parallel to the surface concerned. Then it will generate a shear strain, as shown here. So recall that the largest difference between direct stress and shear stress is that for direct stress, your force is perpendicular to the applied surface. For shear, your force pairs are parallel to the surface exerted. So in this case, when you have a shear force V acting on this surface, then consequently, this fixed surface will give a reaction V in order to cancel it out. When you apply the shear force V onto a surface, then there will be shear stress on it. However, the same to the direct stress, shear stress on the surface is very often uneven. Therefore, we can compute the average shear stress, which is given by tau equals to V divided by A. This definition is very similar to what we just discussed, which is sigma equals to P divided by A. Talk about the Hooke's law in strain. So just now in direct stress part, we know that the Hooke's law is given by sigma equals to E epsilon. This is Hooke's law in direct stress. Now, since we are talking about the shear stress, it has another Hooke's law, which is concerning in the shear stress and the shear strain. Assume your shear force is evenly distributed over the entire region, so that you can have a uniformly distributed shear stress. The Hooke's law in shear stress and strain is given by tau equals to G gamma. Tau is the shear stress, G is the shear modulus, gamma is the shear strain. Just now we introduced that sigma is the direct stress, E is the Young's modulus, where epsilon is the axial strain. Notice that although we have E and G as constant, but in case of shear strain and the axial strain, their constants are very often unequal. That means G is very often unequal to E. For some special cases, and let's have a look of this 2D block under the shear force V. The shear force caused the deformation of this shape, and here is D, here is L. We know that shear strain is actually an angle, so unlike axial strain is non-dimensionalized quantity, which is the ratio between the deformation and the original length. Here, shear strain is also a non-dimensionalized quantity, which is an angle with the unit radian. However, since we know that in radian, tangent gamma is approximately equal to gamma in case the shear strain is small. What is tangent gamma? Well, tangent gamma is significant. It is D divided by L, according to the geometry here. Therefore, in case the shear strain is very small, we can write gamma equals to D divided by L.